Hello students, we discussed units in last class. Now we will see dimensions and find how important role it plays in physics. Dimensions of physical quantities can be defined as the powers to which the fundamental or base quantities have to be raised to represent that physical quantity. We know that force is mass into acceleration, or it is equal to mass into length divided by square of time. Therefore, dimensions of force are m, l, t to the power minus 2. Here force is expressed in terms of mass, length and time, and their powers are 1, 1 and minus 2 respectively. To express physical quantity, we use dimensional formula. Dimensional formula is an expression which shows how and which of the base quantities represent the dimensions of the given physical quantity. Like ml t to the power minus 2 is the dimensional formula for force, and ml square t to the power minus 2 is the dimensional formula for work and energy. When a physical quantity is equated to its dimensional formula, that equation is known as dimensional equation of the physical quantity. Here F is equal to ml t to the power minus 2 is the dimensional equation for force, and E is equal to ml square t to the power minus 2 is the dimensional equation for work and energy. Dimensions of physical quantities have very important role in physics. Dimensional analysis helps us in study of physics through various applications. In dimensional analysis, we check the homogeneity of dimensions in physical expression or equation. In any equation, the dimensions of a physical quantity should be same on both sides of the equation. In fact, unit and dimensions of physical quantities are both treated in the same manner as ordinary algebraic symbols. Identical units or dimensions in the numerator and denominator can be cancelled. Let us now discuss some applications of dimensional analysis. First is, it helps in checking the correctness of the mathematical expression or relation. On the basis of principle of homogeneity of dimensions, it is checked whether the dimensions of various terms on one side of the equation are equal to the respective dimensions of these terms on the other side or not. You can try to check any relation like equation of motion for distance traveled by a moving object. S is equal to ut plus half at square. You will find that each term has the dimension of length, and this proves that the relation is correct. Another application is deducing relation among the physical quantities. Using the principle of homogeneity of dimensions, the relation among physical quantities can be derived, knowing the factors on which the given physical quantity depends. For example, time period of a simple pendulum. We can think whether the time period of oscillations of simple pendulum depends or not on mass m of the bob, length L of the pendulum, and acceleration due to gravity g. Suppose time period t is proportional to m to the power a, L to the power b, and g to the power c. Or t is equal to k times m to the power a, L to the power b, g to the power c, where k is the constant of proportionality. Now we consider the dimensions of all these physical quantities both on left and right side of the equation. The dimension of time, which is simply t, can be written as m to the power 0, l to the power 0, t to the power 1. On the right hand side, dimension of mass is m to the power a, dimension of length is l to the power b, and dimension of g, which is acceleration, is l t to the power minus 2 whole to the power c. Now comparing the powers of m, l and t on both sides, which must be same, we can find a is equal to 0, b plus c is equal to 0 and minus 2c is equal to 1. From these algebraic equations, we get a is equal to 0, b is equal to half and c is equal to minus half. Hence, the time period t is equal to k times m to the power 0, l to the power half, g to the power minus half, which is equal to k times under root L by g. By other method, the value of constant k is found equal to 2 pi. Dimensional analysis does not help in finding the values of constants. This is the limitation of the dimensional analysis. The third application of dimensional analysis is that it helps in conversion of one system of units into another. We know that the magnitude of a physical quantity does not change. It remains the same, whatever be the system of its measurement. That is, Q is equal to N1 U1, which is also equal to N2 U2, where U1 and U2 are units of measurement of the quantity Q in two different systems, and N1 and N2 are their respective numerical values. If M1 L1 T1 and M2 L2 T2 be the units of mass, length and time in two systems, and A, B, C be the respective dimensions of the quantity in mass, length and time on both the systems, then U1 is equal to M1 to the power A, L1 to the power B, T1 to the power C, and U2 is equal to M2 to the power A, L2 to the power B, T2 to the power C. As N2 is equal to N1 times U1 by U2, which is also equal to N1 into M1 to the power A, L1 to the power B, T1 to the power C divided by M2 to the power A, L2 to the power B, T2 to the power C, which can also be written as equal to N1 times M1 by M2 to the power A into L1 by L2 to the power B into T1 by T2 to the power C. Now N2 can be calculated knowing values of N1, M1 L1 T1, M2 L2 T2 and ABC. For example, dimensional equation of force is F is equal to M to the power 1, L to the power 1, T to the power minus 2. Here A is equal to 1, B is equal to 1 and C is equal to minus 2. In SI system, M1 is equal to 1 kg, L1 is equal to 1 meter and T1 is equal to 1 second. And in CGS system, M2 is equal to 1 gram, L2 is equal to 1 centimeter and T2 is equal to 1 second. Then using the equation for N2, you can calculate 1 Newton is equal to 10 to the power 5 dyne. You can try this using dimensional equation of work or energy also, which gives 1 joule is equal to 10 to the power 7 erg. Okay, with this we end the session today. Next day we will begin mechanics. See you soon.